let us start this lecture with a thought process, that is, it is impossible to have an appealing art without a heart. It is very important for us to develop a good heart such that we can live a life and achieve excellence in life. So, let us recall now what we learnt in the last lecture. In the last lecture, I initiated a discussion on ideal rocket nozzle. We made several assumptions which are may not be the realistic one, but however, for simplification of the analysis, we made all those assumptions and derive an expression for exit velocity at of the nozzle, and which happens to function of pressure ratio across the nozzle and chamber temperature and molecular weight of gas and specific heat ratio of the gas. Today, we will be discussing further about it and find out why the shape is like that of a convergent divergent nozzle. As we know that main function of nozzle is to basically expand the high temperature and pressure gas more effectively to achieve maximum exit velocity for getting higher level of thrust. For these purposes, generally we use a convergent divergent nozzle, which is being shown here. If you look at it, is having a convergent duct. This is your convergent duct, and there is another region which will be basically throat, and this area, if you look at, having a minimum area, and then this is portion is a divergent duct, and this kind of nozzle is basically a CD nozzle. And this is also known as the D-label nozzle, or sometimes, or rather most of the times, it is also known as label nozzle, who was instrumental in designing this convergent divergent nozzle in 1888 for a steam turbine. However, today it is being used very much for expanding the hot gas in a rocket nozzle and even sometimes in aircraft engines and wind tunnel, particularly supersonic wind tunnel, and several other places. So, a question might be lurking in your mind, why this convergent and divergent portion? Why not we can have a nozzle which will be having only the convergent nozzle? Let us look at why it is so, considering that let us say this is connected with a reservoir and having the velocity almost will be 0 in this case, because the area will be much higher, which I have not like higher, and the pressure is, let us say PT2. I can consider this as a station 2 and consider this along with the x direction, this is, and temperature T2, this is the reservoir pressure and temperature, and this is your exit plane. I can call it as a E. And let us see what does it happen when you consider a pressure here, what we can call back pressure at the exit of the nozzle, which can be really changed in a laboratory by changing the pressure. But however, when the aircraft or a rocket engine or any other propulsive device moves along with the altitude, then the ambient pressure will be changing, and that is nothing but your back pressure. That means the nozzle will be subjected to variable back pressures. Let us consider now a case where PV is equal to the total pressure in the reservoir. What will happen? You can see that there won't be any flow. If I say this is x direction and then this is the exit plane of the nozzle, that means if I say this is P by pressure, like P by PT 2, and if I say this is equal to 1, and this is the condition, I can say that PV is equal to PA is equal to PT. There is no flow will be taking place. If I draw that another plot over here, this is PV, this is the mass flow rate through the nozzle. We can say there is a no mass flow rate when PV is same as that of the P2. Let us say this point is A, and when PV will be lowered down, that means it is lower than that of the reservoir pressure, that is P2, then there will be certain amount of flow which will be taking place. Let us say this is PB condition, and which is equal to PV and less than PA or PT2. So that flow will be, let us say this is your point B, and in this case the pressure will be changing as you have seen, and velocity will be increasing and density also will be decreasing because pressure is being lowered down. Then let us say a condition where there will be pressure PBC then is lower than the PV, then naturally there will be increase in mass flow rate. Let us consider another case, that P D, where it is much lower than the P C, and such that it will be reaching the maximum flow rate. This is your C, and if I will decrease this pressure further down, let us say P E, which is lower than the P D, but there won't be any change in the mass flow rate. There won't be any change, and if I go for maybe this is your C and this is your D point, this is your E and PF, then naturally there won't be any flow of this thing. That means the mass flow rate will be changing if I join these points. Keep in mind that this condition of the D, which is we call it as a choked condition, choked flow condition. At that condition, the Mach number at this point at the exit will be 1, and this is area corresponding to star, that is choked mass flow rate condition or choked condition, you can say flow condition, and density, temperature and pressure. These are all corresponding to choked condition, and therefore you with this convergent nozzle you cannot really increase the exit velocity beyond 1. That means by using a convergent nozzle one can get maximum speed of sonic velocity or the speed of sound. And if you want to have a supersonic exit velocity in a nozzle, then naturally convergent nozzle is not adequate. So therefore the convergent divergent nozzle is being used, and we will see why we are using that, and for that we will carry out a analysis, and that is for considering the flow to be isentropic. And keep in mind that we will be making all the assumption, we will be making certain assumption. We will be let us restate the assumption what we have made in a little better manner and a more compact manner. The assumption for this analysis what we can have is quasi one dimensional flow. We are saying quasi one dimensional steady isentropic flow. Quasi one dimensional means that in this case the area is decreasing or increasing in a very gradual manner, such that in each location the one dimensional flow is prevailing, although it may not be true generally, but however we are considering that flow to be one dimensional. And isentropic, we know it is basically adiabatic and inviscid flow. So, for that we will be invoking the conservation of mass equation and also the conservation of momentum equation. So, let us consider the continuity equation for quasi one dimensional flow, that is we can write down at any location. If I say this is a particular location, let us say this is your rho P T A, this is the area, and we let us consider that rho A V is constant. Let us now look at this continuity equation in a differential form. That will that becomes d rho by rho plus d A by A plus d V by V is equal to 0. Let us say this is your equation A, and we will now look at for one dimensional isentropic flow the momentum conservation equation is basically rho V dV is equal to dP. This is known as the Euler equation. You might have studied it earlier. So, let us say this is equation B. We will be using equation B and A, and then trying to get a relationship between the area and velocity. Let us now consider the equation B by considering equation B. We can have rho V dV is equal to rho P. We can divide this by rho, and this I can write down dP by d rho into d rho by rho. Keep in mind that this I can write down here, cut here, and this, if you recognize, dP by d rho for isentropic flow is nothing but your A square, and where A is speed of sound. Now, I can also write down here V square here and divide by V. So, if you look at, I can write down this equation as V square by A square. I am dividing that, dV by V is equal to d rho by rho. In place of d by rho, I can write down from equation A, that is minus dA by A minus dV by V. Keep in mind that this V by A basically Mach number, m is Mach number, V by A. So, then this above equation, because this you can write down as m square. So, I can write it down as basically if I take this dV, that will be basically m square minus 1 dV by V is equal to dA by A. So, this is equation, let us say C, and this is known as area velocity. You should keep in mind, and we can also derive a relationship between basically area and the pressure in terms of Mach number. And the importance of this relationship is that which says that if the flow is various regime, that the velocity will be depending on the change in area. For example, if I consider the flow to be very small, let us say when m is tending towards 0, right. So, then m square minus 1 is basically tending towards or minus 1, you can say, because this is almost 0. So, therefore, this from this equation we can get that A v from equation C, we can get that A v is equal to constant. That means is basically incompressible flow. And let us consider a subsonic flow, that is m is less than 1, less than 0, that is subsonic flow. That means m square 1 will be basically less than 0, that is negative, right, because m is lower. So, it will be negative. And this change in the velocity, if it is negative, from this equation we will get for this subsonic flow case dV is negative, and when the dA is positive. That means, if the area will increase, then the velocity will be decreasing, and other way around, if the dA area will be negative, the dV becomes basically will be dV will be positive. That means, there will be accelerating flow. When the area is change in area is negative, that means the exit area is smaller than the inlet area, then naturally there will be accelerating in the flow. The flow will be, and it will be act like a nozzle, and this condition is act like as a diffuser. Let us consider another case, that is the supersonic flow, that is m is greater than 1. That means m square 1, m square minus 1 will become positive, which says that if dA is positive, that means the area will be increasing, that dV will be also positive. If you look at dA is negative, means dV will be negative. What it says that if area will be increasing, the velocity will be increasing, this will be flow will be accelerating, this will be acting like a nozzle, and this one when it is a convergent kind of things, like dA is negative means convergent nozzle, and this will be acting like a diffuser or a and in this case diffuser, the flow will be decelerating. That means at the exit the velocity will be low, and then again pressure will be lowered down as along with the nozzle, along with the diffuser. So, let us consider another case, m is equal to 1, and this is the sonic flow, and in this case the area dA will be 0. That means it can attain area can be maximum, and or it can be also the minimum. Minimum area is basically physically feasible, but whereas the maximum area it cannot really be physically not possible. For example, in this convergent divergent ratio, this area is minimum. So, therefore, if the flow is let us say subsonic here, right, if m is less than 1. So, naturally it will be increasing with the convergent duct, and then after that if it attains the Mach number 1, it flow becomes supersonic, then with the divergent you can get the basically supersonic flow, m is greater than 1, and here m is equal to 1. However, if I consider a case other variant where the area will be maximum, that is this is the kind of thing that you can say this area is a maximum area. Then if the let us say the flow is subsonic here at the inlet, this is your inlet and this is your exit, this is your exit. So, if it is less than, then what will happen? This is the increase in area. So, the dA is basically positive. So, therefore, the velocity will be reduced, that means m became more subsonic at the maximum area condition, and then of course, after that there is a convergent portion. So, it may increase, but it may not reach really supersonic speed because it has not attained a minimum area. So, therefore, this kind of the duct which is having a maximum area in between, so that it cannot act as a supersonic nozzle, and so also a diffuser. So, therefore, that maximum area cannot really be physically possible or is not practicable. So, therefore, we will this is not considered. That is the reason why the throat is there in case of a convergent divergent nozzle, such that we can get the supersonic velocity at the exit of the a D level or level nozzle. So, thank you very much. With this will be stopover. In the next lecture, we will be discussing about how we can relate the area with the Mach number, such that we can see that how we can design and what are the associated problems with that we will be looking at. Thank you very much.